Section 6.3, Gravitational Potential Energy. Now, in the first two sections, we considered the work done by constant forces, something that are pushing or pulling. Now, what about our force of gravity? Can that do work as well? Probably so. So if we imagine a ball, like a basketball or tennis ball, and we look at the force of gravity acting on it, the force of gravity is pulling down on it with a magnitude of mg. If that object is moving down in the same direction as the gravitational force, then we could calculate the work done by gravity by knowing that the work done by gravity will be the gravitational force, mg, times the cosine of the angle between the force and the displacement. So assuming we're going down, they're in the same direction. And cosine of 0 degrees is just 1. Displacement is the initial height minus the final height, because that will give us this value s, right? If we have h is the bigger quantity minus hf is the final quantity. So that tells us the work done by gravity is equal to mg times the difference in height, the initial height minus the final height. And this feels a little strange. Some people have wondered, why do we have initial minus final? Because in every other case, we usually have final minus initial. Why the reversal here? Well, the key is this is just trying to represent the displacement, s. And s in this case is positive. So the way that we keep this positive is we do the larger number, the initial height minus the final height, since we're going down. So it's just something to focus on getting the right proper distance here. So hopefully that helps you some. And an interesting thing is it doesn't actually matter if the ball goes straight down. Pretty strange, right? So it's possible that the ball could go up and then go down, or even go up and sideways and then down. Like this path here, right? Where it's arcing up and then down. The only thing that matters when we're calculating the work done by gravity is the amount of the difference in the height, because the height is in the same direction as the force of gravity. So we just care about those endpoints and not the path from one to the other. And we're going to use this definition of the work done by gravity in order to introduce our gravitational potential energy. So our definition of gravitational potential energy, which is often abbreviated as PE, the gravitational potential energy, PE, is the energy that an object of mass m has by virtue of its position relative to the surface of the Earth. That position is measured by the height h of the object relative to an arbitrary 0 level, right? So you have some level that you set is equal to a height of 0, and so then you measure the height to some point of interest, like the ball, and that can tell you that the potential energy of said ball is the mass of the ball times g times the height. mgh is our potential energy. This is another equation that pops up very frequently, so it's another good one to lock into your crib sheet, your memory, all of the above. If we check the units of it, mg is a force, so that will have units of newtons, times h, that's a distance, that's going to have units of meters. So newtons times meters, what unit does that give us? The joule! So once again, this is an energy, and so it has units of joules. A good clarification with this is potential energy is a little bit of a strange term. It's like, does it not actually have energy? And the use of potential there is saying that it has the potential to create kinetic energy. It still definitely has energy, depending on your reference frame where you set the height equal to 0. And that energy can create motion, which is our kinetic energy. So let's take a look at an example of this in action. So this is an example from the end of the chapter problems, number 29. 75 kilogram skier rides a 2,830 meter long lift to the top of a mountain. The lift makes an angle of 14.6 degrees with the horizontal. What is the change in the skier's gravitational potential energy? All right, so this is a good problem. It's one that I want to go back to our process of starting with a picture, because they don't give us a picture here, and I think that would really help. So there's a lift that's going to the top of the mountain, and it says it makes an angle of 14.6 degrees with the horizontal. So you can draw in the horizontal here, and 14.6 degrees, right? And I'm going to start to make a triangle, because I really like triangles. You could also try and draw a chairlift. That's a little bit harder to do. Let's see, we got our legs with the skis, and a body, arms, and kind of a head, no neck there. Cool, so we have the chairlift. And it tells us that the angle is 14.6 degrees. So we have that. It also gives us one of the dimensions of this triangle that we've created. We always like to make triangles when possible. It says the lift is 2,830 meters long. Now, is that describing the horizontal distance, the vertical distance, or this diagonal? Well, it's describing the distance of the lift, so that's going to be the diagonal, right? 2,830. Cool, so that's a great thing to fill in. What else does it give us? It says the 75 kilogram skier. It's saying 75 kilograms, that's telling us once again, that is the mass of the skier. So we know M. Great. What are we trying to find? We're trying to find the change in the skier's gravitational potential energy. So we could write that as a delta. The Greek letter delta represents change in potential energy. Right? All right, well, how do we calculate change in potential energy? Well, our change in potential energy is just going to come from mg, the force, times the change in height. However much that changes. So we could also write our change in potential energy is equal to mg times h final minus mg times h initial. And if we set our initial height as being equal to 0, then the second term just goes away because HO is equal to 0. So all that we care about then is the final height, which would be at the top of our triangle and measured relative to the initial height. That's the other side of this triangle, right? The height of the triangle. So we know the mass, we know G is our constant, 9.8 meters per second squared. What is our HF? That's where we're going to need some trigonometry to help us out. We have this angle, and we have the length of the top of the triangle, the long side of the triangle, the hypotenuse. So what trig function can help us relate this side that is opposite the angle to the length, to the hypotenuse? It's going to be sine, right? We can see that sine of 14.6 is going to equal the opposite, which we could call h sub f, divided by the hypotenuse, 2,830 meters. So the final height is just 2,830 meters times sine of 14.6. So we can get our change in potential energy by calculating the mass, 75 kilograms, dropping the 0.0 just for space sake, times 9.8 meters per second squared, times this 2,830 meters, and times sine of 14.6. Almost off the screen there. All right, so if you calculate all of that out, you should ultimately arrive at something like 5.24 times 10 to the fifth. Wow, that's a big number, right? That's 524,000 of its change in gravitational potential energy. Very impressive, but it's meaningless without units. So what units do I need to fill in here? It's joules! So we need the joules in order to finish our answer, and there we have solved number 29 from chapter 6, which demonstrates gravitational potential energy.